Topic is uncertainty estimates, the new editorial standard, and I think this is relevant to our discussions because in order, if we do develop new procedures or ways of evaluating uncertainties, it's in order to implement this, it's going to require the input and cooperation of the journal editors and the referees. Otherwise, nothing is going to happen. So I'll present the point of view from Physical Review A, an experiment that we've had in progress for the past few years. And of course, David Schultz is also here from Atomic Data, Nuclear Data Tables, and so you will also be participating in this as an editor. So just in terms of the history, I've been interested in this problem for a long time. It occurred to me that there's this imbalance between theory and experiment and the expectations in terms of providing error estimates. And so I've been interested in this ever since I became the editor of PhysRev A in 2007. It became, in the 2010 ITAMP data meeting, there was a panel discussion on this where I presented my ideas on it. And in fact, this was published in the conference proceedings. There was a panel discussion where we discussed the possibility of introducing a new editorial standard, and there was quite strong support for the idea, so we decided to go ahead with it. And an editorial announcing this new standard was published in 2011, and I've distributed that. How many people have actually seen this or were aware of its existence? Yeah, actually quite a few. Glad to see that people at least occasionally read the editorials that we publish. It doesn't just fall on deaf ears. So the outline of my talk, background and rationale, then the policy statement itself, implementation, and then I can update this now with recent examples and statistics. And I might say also that the enthusiasm for this has been somewhat muted among the associate editors. And so this is something that we're going to have to keep in mind, that even though we might think it's a good idea, the implementation is not going to be necessarily smooth sailing. So in terms of the journal and its goal, we wanted to keep it in step with the community of users, and we have a policy of rejecting about 20% of papers without external review if they don't meet our standards for publication. And so what about extensive tabulations of data? This is, of course, very useful, but does it contain new physics? This is the goal of physical reviews, to publish new physics. And so the critical evaluation of data can be interpreted as involving new physics. That if you develop new ways of doing it, or more reliable ways, then that is making an important contribution to the physics community. And the authors themselves are in the best position to do this critical evaluation, and it can, not necessarily, but it can in fact qualify as satisfying the criterion for new physics. And so the mission of PhysRev A, as I was just saying, is to publish significant advances in physics, advances in techniques for the evaluation of data, and uncertainties would qualify as new physics. And its role in other journals, such as Atomic Data, Nuclear Data Tables, to apply methods to extensive tabulations of data. So these are really different roles for the two journals, and so keep that in mind when we talk about the implementation. So in the broader context of the evolution of physics, the hallmark of good physics is, of course, that theory and experiment progress hand in hand. It's one of the great strengths of physics as a discipline. In a new field, the role of theory is to provide a qualitative explanation of experimental observation. So when new phenomena are first observed, you just want to understand what's going on. But as the field matures, the focus shifts to high-precision comparisons between theory and experiment. And so different areas of physics are at different stages in this process of evolution. And eventually, small deviations is what you look for to reveal new physics. The classic example of that is the detection of the planet Neptune from tiny deviations of the orbit of Uranus from the expectations. Currently, the proton size anomaly has received a lot of publicity, including a cover story in Scientific American. But here, this is another role in which uncertainty estimates are crucial, not in applications to plasmas, but in looking for new physics. So that's a separate role for uncertainty estimates. So in addition then to looking for new physics, in this sense, to apply observations in other areas. And so, of course, we now have the emergence of many databases. These are just the ones I know about. There may be others, and so the evaluation of the reliability of the information in these databases becomes of critical importance in their application. And so a new profession of expert evaluator has emerged to assess the accuracy of these databases. But in most cases, the authors themselves and the referees are the best and most knowledgeable people to perform this task. And so that's where the journals come in. Perhaps the journals have a role to play in expecting a higher standard of assessment. So as I mentioned, we had this panel discussion at the 2010 ITAMP data meeting, where there was a general consensus to introduce a new editorial policy. So the policy statement itself, this is the preamble where I discuss the current, or at least until recently, what was the usual standard for the field is that experimental papers are required to have a carefully evaluated error budget, but the same is not true of theory. The culture is often just to publish long strings of numbers with no indication of their uncertainty or how many figures are in fact physically meaningful. And an experiment, the determination of these error bars is often the most difficult and time-consuming part of the experiment. Theorists sometimes complain, well, it's difficult to identify the uncertainties. Well, sure, it's difficult. It's also the most difficult part of an experiment. And just because it's difficult doesn't mean it shouldn't be done. And so even papers, experimental papers reporting entirely new phenomena usually contain enough information to convince the reader that the effect is in fact real. So the question is, to what extent can these same high standards be applied to papers reporting the results of theoretical calculations? And here is where this point about it being difficult. Should this be considered an adequate reason for omitting them? So in order to answer this question, we need to consider the goals and objectives of theoretical work being done. So I've tried to classify theoretical papers. And so not all of these are suitable for a requirement of uncertainty estimates. Development of new theoretical techniques, development of new approximation methods, explanation of previously unexplained phenomena where semi-quantitative agreement is already useful and interesting, proposals for new experiments. So it's the last two that we're really focusing on. Quantitative comparisons with experiment for the purpose of verifying that significant physical effects have been taken into account and or be interpolating or extrapolating known experimental data. And also provision of benchmarks, benchmark results intended as reference data or standards of comparison with less accurate methods. So it's in these last two categories. There's a lot of misunderstanding as to what we mean by requiring uncertainty estimates, and people think it applies to all of these things and say, oh, it's just impossible, it can't be done. But if we restrict our attention to places where it is meaningful and possible, then we can make progress. And so it's primarily papers in these last two categories, and as Hyung already has pointed out, there are two sources of uncertainties. One is the degree of convergence within a given calculation assuming some underlying physical content. Convergence with the size of the basis set, or so on, step size and numerical integration. But secondly, and this is like the statistical error in an experiment, but there's also the systematic error that comes from physical effects not included in the calculation, such as electron correlation or relativistic corrections. And so, of course, it is never possible to state precisely what the error is without, in fact, doing a larger calculation. And again, this is a source of uncertainty that people think that we want a rigorous error bound or a definite value of the between uncertainty and error, that the error is a given amount. In order to do that, you in fact have to do a larger calculation. So the aim is to estimate the uncertainty, not to state the exact amount of the error or provide a rigorous bound. It's also important to remember that if you consider physics that hasn't been included, it's actually a bimodal distribution. For example, if you do a non-relativistic calculation and then estimate the relativistic corrections, the most probable value is not 0. If the errors are, let's say, of order alpha squared, fine structure constant, then that means you expect some deviation, and the most probable value for the relativistic corrections is not 0, it's some finite value. And so it's not a Gaussian distribution, and so you can't treat it as it's important to remember that when doing statistics on the uncertainty estimates themselves. Also, an issue of how to express the uncertainty. What would you consider to be sufficient or an adequate statement? Actual error bars on the data, you might call that the gold standard. And then after that, categorizing the uncertainties as A, B, C. This is sometimes done in the NIST tables or older NBS tables, where oscillator strengths, for example, were categorized into different categories. That's of course also a useful estimate of the uncertainty, but it's not quite the same standard. And then finally, sometimes authors do this and think that they've satisfied the requirement that, for example, we believe the data in the tables are accurate to better than 10% without actually putting any error estimates into the uncertainty estimates into the tables themselves. So it's better than nothing, but is that good enough? Would you really expect more than that? And so there are many cases where it is indeed not practical to give a meaningful error. For example, in scattering processes involving complex systems. And that's going to be a main topic for discussion here at this meeting. What progress can we make in areas such as that? The comparison with the experiment itself provides a test of our theoretical understanding. But there is a broad class of papers where the estimates of theoretical uncertainties can and should be made. And so our policy is intended to cover these cases where theoretical uncertainty estimates are practical without placing undue restrictions in cases where the policy would be inappropriate. And so so now comes the policy statement itself. That papers presenting results of theoretical calculations, this is what I've just distributed, so you have it as a hard copy, are expected to include uncertainty estimates for calculations whenever practicable, and especially under these circumstances if the authors claim high accuracy or improvements in the accuracy of previous work. If the primary motivation is to make comparisons with present or future high-precision experimental measurements. And this is often the case when you're looking for, let's say, evidence for parity non-conservation or variations in the fundamental constants, cosmological variation, or electron-electric dipole moment, things like that, then this is the other context in which these uncertainty estimates are of great importance. Or if the primary motivation is to provide interpolations or extrapolations of known experimental measurements. And that's often the case for the plasma modeling and astrophysical applications. And so what is our current procedure? In order to implement this, we have a memo that we send out if a paper comes in and it doesn't meet the requirements. We send a memo that before we seek external review, we ask you to please take note of the attached memo regarding the need for uncertainty estimates for theoretical papers. So the paper doesn't even go out to review, out to referees until this has been done. And so, in other words, we put some teeth into it. It's not just added on as an afterthought. The referees themselves get to see the uncertainty estimates and comment on whether or not they are it's been properly done. And in fact, the response to this has been quite good, at least within the areas where we've been able to implement this. So we've about 100 papers have been affected by this. No papers have been withdrawn. The authors have said, well, I can't do this, it's impossible, I'll go someplace else. And in fact, the community involving atomic structure and oscillator strength type work have really taken this to heart. And standard software packages have in fact been modified to retain information needed to make the uncertainty estimates. And so now the authors are starting to police one another, and so the papers are now coming in much more with the uncertainty estimates already included, and so the need for this memo that I just showed you is in fact decreasing. The recent example, Mariana Safranova has particularly taken this to heart, and I think has set a good example of what can be done. This is a paper from 2011, but she's continued on maintaining this higher standard of publication, and many other authors have also followed suit. So as a consequence, papers are more interesting and have greater impact. AMO physics as a field acquires greater significance and importance because of the applications. And the culture of the field is changing so that inclusion of uncertainty estimates become the new norm, at least in some areas involving structure and spectroscopy. Oops. So let's look at some. So the next steps are then to define more fully a set of protocols and best practices, and that's what we're here for today. Publicize and promote this. So let's see what's actually happened over the past 3 years. These are the number of uncertainty memos sent to authors. The blue bars are those initiated by the editors, but then sometimes the referees themselves call for uncertainty estimates. And you can see that the number, that 2011, a lot of memos were sent out, 2012, but it's become less necessary since 2013. So this indicates the degree to which these new standards are being adopted by the community, at least within a range of papers. So here, this gives you an idea of the distribution by subject matter. First, this is atomic compared with molecular. It's mainly in atomic physics rather than molecular, where the memos have been sent out for uncertainty estimates. Atomic spectra, relatively little for scattering. And so this is where there's been a lot of, this isn't because the papers don't need it, it's because the editors handling those papers feel reluctant to send them out. So this is what is happening, that the spectroscopy part is under fairly good control, but not scattering. And for few body relative to many body, it's mainly in the many body paper, so you can read across here. It's mainly for atoms, spectroscopy, many body. So that's where most of the action has been. And there's been, well, for few body products, hydrogen, helium, lithium, there's been less need for it because it's already more the practice in those areas. And for scattering theory, there's just reluctance to send the memo to begin with. So as of course, it's a relatively small fraction of the total articles published in PhysRev A, A3, this is the atomic structure and spectroscopy. A4 is scattering theory. So you can see that there's 200 or 300 papers in each of these categories. And most of the papers are in this area. Of course, this includes experiment as well as theory. So that gives you an idea of what fraction of the papers are being affected. And this just it says again what the different areas are. A3 is atomic structure, dynamics. A4 collisions and interactions. A few papers involving fundamental concepts, theoretical calculations of for high precision comparisons with experiment. But the other areas really don't enter in. Quantum optics, of course, it really isn't appropriate to even talk about this for some areas of physics. So this is a summary of editorial opinion. I said there was resistance to implementing this, and this summarizes a statement. I won't say who this is from, but it's from the collection of statements. That basic question rests with estimation of convergence errors and systematic errors. As I've already said, the former can be determined and refined. However, one is always faced in larger systems with approximations to the basic formalism which do not lend itself to a perturbative expansion. This is the key point here, perturbative expansion. One is left with relaxing these approximations in some systematic way. However, from experience, in the few cases in which we have very accurate measurements, sometimes increasing the accuracy of one component makes the agreement worse. And so that's the kind of difficulty that you're faced with in requiring or demanding uncertainty estimates. And this also goes back to the degree of maturity of the field. To what degree is the basic physics really under control and understood, and computational methods for handling it. So it made it just a problem of maturity of the field that is entering into here. And so that is something that we really need to grapple with in our discussions in this workshop. And he concludes by saying, I have not used the editorial statement in regard to scattering calculations for these reasons. So that's a pretty clear statement. So what we need to do is to have a credible policy that people will buy into and implement when papers come in and are reviewed by the editors and referees. Just might be interested to see some recent examples where the memo was sent out, potential energy curves, dipole moment, radiative lifetimes of the potassium-beryllium molecule. The next two were in fact error bars were requested by the referee involving scattering. So it's interesting that some pressure is coming from the referees to include error bars for both of these involve long-range collisions and electron scattering. And the others are again, more structure-type papers, relativistic effects, hyperfine structure, radiative decay from doubly and singly excited states, Hilarious CI analysis of low-lying states, and 3-electron lithium and beryllium plus. So this is certainly a case where you'd expect to have a well-defined uncertainty estimate, and the paper would simply not be publishable without it. So, in conclusion, the aim is not to be excessively rigid or make unreasonable demands. The aim is just to expect a realistic assessment of accuracy in theoretical calculations when the field has reached a high degree of maturity, and it is perfectly possible to do so. Journals have a lot of influence in encouraging authors to give properly justified uncertainty estimates, and the culture has indeed changed in some areas, as we've seen, but not others. Improved techniques are needed, especially for scattering problems, and there's still considerable resistance from editors to require uncertainty estimates for scattering calculations.